Alright, so a short video on oxygen and carbon dioxide transport. If some of the terminology that I'm using here doesn't really click with you and you're not comfortable with it, then I want to encourage you to go back and read through the slides in the textbook so that you understand what I mean when I say partial pressure gradients. That's an important idea. And briefly, just like air movement follows a pressure gradient for ventilation, there's this idea called partial pressure. And partial pressure is the contribution from a particular gas into a mixture. And partial pressure gradients help us understand the difference in concentration of these gases at different points along the circuit. And so the partial pressure of oxygen and the partial pressure of carbon dioxide, the gradients that are set up here are pretty much intuitive. They're pretty much what you would guess or hope would happen based on the function of the system, which is to bring oxygen from the alveoli, from the atmosphere, to the tissues that need it, and to load the waste products of carbon dioxide back into the blood and bring it back to the lungs for elimination or exhalation. So I like to start by thinking about oxygen, follow it all the way around, and then I think about carbon dioxide in a different color. And I start in the tissues and I follow it all the way around. I also want to remind you that the capillaries that surround alveoli and the capillaries that are in the very smallest branches of the blood vessels out in the tissues, they have two sides. They have an arterial side and a venous side because they're part of a circuit. And so these branch into very little tiny branches, but then at some point they start to branch back into larger and progressively larger branches on the venous side or the arterial side, depending on which direction you're going. So I start to think about oxygen at the venous side of the pulmonary capillary, and the partial pressure of oxygen in the alveolus is about 104. And the partial pressure of oxygen in the blood right here, having been returned to the lungs from the body, is about 40. So you can see there's an obvious difference in these partial pressures for this gas, and so gas naturally will move along its partial pressure gradient and it will diffuse across the respiratory membrane into the blood of the pulmonary capillary, which is flowing in this direction. Here, where the capillaries have started to increase in size into larger and larger branches as they move back toward the what's called the systemic circulation, the partial pressure of oxygen has equilibrated. So there's no net flow of oxygen back and forth at this part of the blood vessel, because that's the whole point. It diffuses until it's equal, and there's plenty of supply of oxygen here for equilibrium to be achieved. And now at this point, all that oxygen has been loaded onto a bunch of hemoglobin, and it's going down the river or going down the train track, however you want to think of it. At some point in this circulation, we're going to review it in the cardiovascular section, but deoxygenated blood from the bronchi enters this stream, and so it lowers the partial pressure of oxygen somewhat, but it's still quite high. And you'll notice that by the time we reach the arterial side of this capillary bed, at the level of these tissues, the partial pressure of oxygen is substantially higher than the partial pressure of oxygen in the tissues, which is about 40. And so again, the partial pressure gradient is obvious. Oxygen diffuses out of the blood into the tissues where it's used. And by the time we complete this process, at the other side of the capillary bed, in the venous side of the capillaries, the partial pressure of oxygen has equilibrated, and it's 40. And it's 40, even Steven. And this relatively deoxygenated hemoglobin and all these red blood cells are now in the venous circulation, traveling back to the right side of the heart, which pumps that blood into the pulmonary circulation up next to an alveolus so that it can be reloaded with more oxygen. Okay? If we think about this process from a carbon dioxide standpoint, carbon dioxide is the waste product that exists in the tissues, and it's toxic if it reaches certain levels, and so it's important to offload it back into the tissues, and that happens at this level on this arterial side of the pulmonary, of the capillary bed, sorry. And the partial pressure of carbon dioxide at this level is about 40. And the partial pressure of carbon dioxide in the tissues is higher. It's about 45. And the concentration, the partial pressure gradient moves in this direction, which is what we hope. We hope that the waste product would diffuse into the blood so that it can be brought to the lungs to be eliminated. And the same type of equilibrium is established for, excuse me, sorry, for carbon dioxide as it is for oxygen. Okay, so it's important to point out this equilibrium that happens here, because equilibrium is established, we're not undoing all the work we just did and just dumping the carbon dioxide back or dumping the oxygen back into the blood. Okay, so the carbon dioxide is now traveling on the vein train, as we say, back to the right heart, where it's pumped into the lungs. And recall that the vast majority of carbon dioxide is traveling inside erythrocytes as bicarbonate ion. And we'll review that, I think, probably in another video, but that's the form that it's in. And then here is converted back to carbon dioxide, and the partial pressure gradient of carbon dioxide at this level on the venous side of the pulmonary capillary bed is 45. And the partial pressure inside an alveolus for CO2 is about 40. And it's able to diffuse out of the pulmonary circulation, out of the blood, across the respiratory membrane, into the alveolus. There it's expired. I think it's important that you guys can draw this type of diagram, and that at these points you can describe the partial pressure gradients for both oxygen and carbon dioxide. I think it's important that you understand why the partial pressure of oxygen is slightly lower by the time it reaches the tissue as compared to when it first entered the bloodstream. That's the input of deoxygenated blood from these structures. We're going to talk about it more, but I want to introduce that idea to you now. And again, I'm not going to go into it in this video, but I want you to remind yourselves as a part of this, how exactly is oxygen carried? It's carried bound to hemoglobin. Sorry. It's bound to the 4 subunit protein, which is my favorite, called hemoglobin. And hemoglobin, of course, has 4 seats for oxygen. going to talk more about the structure of hemoglobin today, but oxygen is bound to hemoglobin at this level. Here, oxygen is offloaded from hemoglobin, and the red blood cells are passively pumped along the circuit, but when they reach these areas where these concentration gradients exist, the gases can't help but dissolve along the concentration gradients. That's nature. That's the universe and how it works. Sorry about that. So I just wanted to demonstrate how I draw that and explain it in a little bit shorter time than I did before. Do it yourself.